Hello everyone, this is Balashwita. In this video, I'm going to discuss about Fleury's algorithm, which helps us to find Euler paths and circuits in a graph. First of all, let us understand what are Euler paths and Euler circuits. Euler path. An Euler path is a path that visits every edge exactly once. In the image, 3, 4, 1, 2, 0 are vertices, and the line between the two nodes is an edge. Now again coming back to the definition, it is a path that goes through every edge of a graph exactly once. In the image, to find Euler path, let us start at vertex 0. Now from 0, I can go to 1, and from 1 I can go to 4, and from 4 I can go to 3 or 2 but not 1 because we already visited that particular edge, and from 4 I can go to 2, and from 2 I can go to 3, and from 3 and I can go to 4. Here we visited all the edges. Now the Euler path is 0, 1, 4, 2, 3, 4. And now coming to Euler circuit, an Euler circuit is a circuit that traverses every edge exactly once, starting and ending at the same vertex. This is same as Euler path, but the condition is the starting and ending vertex should be the same. It is also a Euler path that starts and ends at the same vertex. In the example, A, D, E, B, C, E, F are vertices. Here we are starting at A. From A, I can go to D or E or C or B. Here I am going to E. From E, I am going to C. And from C, I am going to A. And from A, I am going to B. And from B to C, C to F. And from F to E, E to D. And finally, D to A. Here we are starting at A and ending at the same vertex A. So this is a Euler circuit. There are some conditions for Euler circuit and path to exist in a graph. If a graph has more than two vertices of odd degree, then it has no Euler path. What is a degree? Degree is nothing but the number of edges incident on that node. If a graph has 0 or exactly two vertices of odd degree, it has Euler path. If a graph has 0 vertices of odd degree, then it has Euler circuit. These conditions are very important. Now the question is, why do we need this? Are they really helpful? Yes, here I have shown some of their uses. They are used in network design, circuit board testing, DNA sequencing, graph theory and algorithms, puzzle solving, and many more. You can go through the slide. And next, coming to Fleury's algorithm. To understand Fleury's algorithm, we also need to understand the term bridge. Bridge in a graph refers to an edge whose removal increases the number of connected components in the graph. Or bridge is an edge which disconnects the graph. In the example, if I remove the edge 3, 4, the graph becomes disconnected. So this is a bridge. And if I remove any other edge like 1, 2, does this affect the graph? No. Even if I remove the edge 1, 2, I can go to 2 in this way, from 1 to 3 and from 3 to 2. This is not a bridge. Now let us understand the Fleury's algorithm. It is a method for finding Euler paths and circuits in a graph. It ensures that every edge is traversed exactly once except for bridges, and that the algorithm terminates when all edges have been visited. Now let us see the steps to find Euler path or circuit in a graph. First of all, we need to select a starting vertex. Choose a starting vertex as the current vertex. If there are 0 odd vertices, start anywhere. If there are 2 odd vertices, start at one of them. If it has 0 odd vertices, then it has Euler circuit. Or it has 2 odd vertices, it has Euler path. Remember this point. And then we need to traverse each edge. If it has multiple edges, then avoid bridge. And then after moving through that edge, remove that edge. repeat the same process until there are no edges in the graph, and again check for the completion. If all the edges have been traversed, then it has Euler path or circuit. If not, it doesn't have Euler path or circuit. There are some rules in Fleury's algorithm while selecting edges. When a vertex has only one edge, that edge must be traversed to avoid leaving the vertex isolated. When a vertex has multiple edges, the algorithm avoids choosing a bridge. We already discussed what is a bridge. This ensures that the graph remains connected until all edges are traversed. Now let us see an example. Now first we need to select the starting vertex. Let us check the degrees of each node. Vertex 0 has degree 4 and vertex 1 has degree 2, vertex 2 has degree 4 and also vertex 3 has degree 2, vertex 4 has degree 4 and vertex 5 has degree 2. So all vertices has even degree. So there are 0 odd vertices. So it has Euler circuit. Again I am repeating the point, all the vertices has even degree, so it has Euler circuit. So we can start from any vertex. Here I am starting at vertex 0, and from 0 I can go to 1 or 2 or 4 or 5. I can select any edge because there is no bridge. Here I am going to 1. Now the path becomes 0, 1. From 1, I can go to 2 because there is only one edge. Before going to 2, remove the edge between 0 and 1. Now the path becomes 0, 1, 2, and I remove the edge between 0 and 1. From 2, I can go to 0 or 4 or 3. And now I'm going to 3. I'll remove the edge between 1 and 2. So the path becomes 0, 1, 2, 3. And from 3, now I can go to 4 because there is only one edge. And I'll remove the edge between 2 and 3. Now the path becomes 0, 1, 2, 3, 4. And from 4, I can go to 5 because there is only one edge. And I'll remove the edge between 4 and 3. Now the path becomes 0, 1, 2, 3, 4, 5. And from 5, I can go to 0. And I'll remove the edge between 5 and 4. Now the path becomes 0, 1, 2, 3, 4, 5, 0. Here, some of you will get a doubt that before I said we should visit only once, but now again vertex 0 is in the path. The condition is visiting every edge exactly once, not the vertices. So we can go from 5 to 0. And from 0, I can go to 4 or 2. I'm going to 2 and I'll remove the edge between 0 and 5. Now the path becomes 0, 1, 2, 3, 4, 5, 0, 2. And from 2, there is only one edge. I will go through that. Here again from 2 I can go to 4 and I'll remove the edge between 0 and 2. Now the path becomes 0, 1, 2, 3, 4, 5, 0, 2, 4. And from 4 I can go to 0 and I'll remove the edge between 4 and 2. Now the path becomes 0, 1, 2, 3, 4, 5, 0, 2, 4, 0. And from 0 I cannot go anywhere because there are no edges. So now the circuit becomes 0, 1, 2, 3, 4, 5, 0, 2, 4, 0. This is the Euler circuit. Now let us see the code implementation. Here I have implemented the code in Python. Let us check the code. Here I have used mainly 5 functions. The first function is find start vertex. It finds a suitable starting vertex for the algorithm by checking for vertices with odd degrees, returns a vertex with an odd degree if found to ensure the existence of an Euler path or circuit. And the second function is bridge. It checks if an edge between vertices u and v is a bridge by determining if removing it disconnects the graph, returns true if the edge is a bridge, otherwise false. And the third function is edge count function. It calculates the total number of edges in the graph by summing the degrees of all vertices, divides the total count by 2 as each edge contributes 2 to the total degree. And now the main function is Fluery algorithm. This is the main function where the actual implementation works. Implements Fleury's algorithm to find an Euler path or circuit in the graph, uses a list path to store the edges of the Euler path or circuit. It uses a flag circuit found to track whether an Euler circuit has been found. And the last function is process graphs function. It reads a graph from a file and processes it using Fleury's algorithm to find an Euler path or circuit, prints the result for each graph in the file, and handles the processing of the last graph. In this graph, the input is taken from a text file. Now I'll show you the input file. These are the inputs, and now I'll run the code. This is the output. And now coming back to the slides. We have already seen the description of each function in the code. You can go through it. And next, going to the next slide. This is the screenshot of the output. And next, coming to the time complexity analysis. Now let us see the time complexity of each function. The first function, finding the start vertex, takes big O of v time. And the next function, checking if an edge is a bridge function, takes big O of e time, where e is the number of edges and v is the number of vertices. And the next function, counting edges, take big O of e time. And next function, Fleury's algorithm, which is the main function, it takes big O of e square time. So the overall time complexity becomes big O of v plus e square. Removing the less dominant terms, now the time complexity becomes big O of e square in most cases. Now let us analyze the worst case and best case time complexity. The best case time complexity, it occurs when the graph has an Eulerian circuit or path. In this case, the algorithm selects edges without creating bridges, leading to a linear time complexity of big O of e, where e is the number of edges in the graph. So the best case time complexity is big O of e. Now coming to the worst case time complexity, the worst case scenario occurs when the graph has no Eulerian circuit or path, and the algorithm encounters bridges at every step. In this case, the algorithm may need to explore all possible edges at each vertex, leading at a time complexity of big O of e squared, and we already know e is the number of edges. So the worst case time complexity is big O of e square. Now coming to space complexity is big O of v plus e, where e is the number of vertices and e is the number of edges. The space complexity arises from the need to store information about visited vertices and edges during the traversal process. And next, finally, applications of Fleury's algorithm. They are widely used in network analysis, circuit design, DNA sequencing, and robotics, computer networks, and many more. You can go through each point. And next, finally, conclusion. Fleury's algorithm is a valuable tool in graph theory for finding Euler paths and circuits. It provides an efficient way to traverse edges in a graph while ensuring that each edge is visited exactly once. Thank you. I hope you enjoyed the lecture. Please do like, share, and subscribe for more videos.